Hello everyone, my name is Darpan Verma. I work at the Ohio State University with Dr. Roberto Myers. Today, I will be going to talk about a technique that we have developed in our lab to measure and map the electric field for power electronic devices. An example case that I am going to cover today is for gallium nitride PN junction diode. This work is also published in Applied Physics Letter recently, and you are most welcome to have a look or contact us for any collaboration. The outline of the talk would be as follows. First, I'll be going to talk about Franz-Keldysh effect for field measurement and its discrepancies. Then we'll see the exciton modified Franz-Keldysh effect used for gallium nitride. I'll also talk about the inclusion of quadratic Stark effect for excitons in the depletion region. And then finally, we'll see field measurements, results, and for the particular gallium nitride junction devices, and then summary. Walter Franz and Leonid Keldysh gave a theory for optical absorption, according to which under uniform electric field, band-to-band transition of carriers can take place, even with below band gap energy photons. This happens due to the wave function penetrating into the forbidden region, which is schematically shown in this figure here. As we all know that band bending under electric field have a proportionality relationship with the field, and this can be seen in the absorption coefficient data as well, that incurs band bending into the absorption coefficient. This broadening of the photocurrent spectra, that is a signature of the band bending, can be used to measure and map the field of power electronic in case of power electronic devices. Such a broadening in the spectral photoresponsivity below the band gap have been reported in many cases for gallium nitride photodetector study. As seen from the study by Shen et al., the broadening with the increasing reverse bias can be clearly seen here. Similar study by Wang et al. Showed such effect with the increasing reverse bias. Now, using constant excitation wavelength, Maida et al. Have showed that by using Espinet's Franz-Keldysh model, fields in the depletion region can be calculated. They used constant excitation wavelength, and the constant excitation wavelengths basically are marked with the red lines here. So 390 nanometer represent this particular line here, and then 420 nanometer represent this particular line here. So these points are basically collected at different curves on this particular plot. These excitation wavelength gives the fit, which was amazing, but this complete spectral variation of photoresponsivity cannot be described by only band-to-band Franz-Keldysh Espinet's model. We actually tried to take the measurement for which we used all reflective optics, that is without any achromatic aberration, and illuminated a device at a particular location here. This illumination of device is schematically drawn here, and the axis represents that the z-axis shows the depletion width, the xy position shows that by moving the xy position you can basically move on the device like this. Let's consider now we are at a position pxy. The responsivity spectra taken at this particular position pxy can be seen here. This responsivity spectra shows that there is an excitonic peak red shifting. This is on the linear scale, and the tail broadening can be seen, which is Franz-Keldysh effect on the logarithmic scale. Now, how do we know this is excitonic peak? We know because there are many reports on gallium nitride which shows that there is a nice peak of at around below the band gap in case of gallium nitride at room temperature. And the binding energy for this exciton carriers are around 20.3 to 27 millielectron volt, which is quite high. Finally, using Espinet's Franz-Keldysh model, we basically try to fit our spectra. This spectra, it is to be noted that this spectra gives us a nice fitting of around R square 0.90, but the values which we get for the local voltages. Now, what is this local voltage? This local voltage is the only free parameter used by employing all the first principle values for gallium nitride, like binding energy, band gap, effective mass, etc. Finally, we get the local voltages values and plot them with respect to applied voltage, and we get a linear fitting. When we extrapolate this line, we see that it gives us VBI. Now this VBI comes out to be 15.2, whereas the 1 by C square versus V plot gives us the VBI of 3.2. Therefore, this Espinez-Franz-Keldysh model was failed to explain why the built-in voltage measured at this particular location was different. Therefore, we try to incorporate the model given forward that includes the excitonic effect. So basically, when there is electron and hole coupling, interaction between carriers can be seen forming a potential well, as I have shown you here. Now, with and without field, when there is no field, the carriers are trapped in these potential well. But when there is field, the carriers can easily go out of these fields. And Dow et al. In 1970 showed this effect, according to which when you have like zero field, you will have a sharp peak. But when you increase the field, this peak would keep on reducing and there would be a definite broadening in the peak. However, in gallium nitride, we saw that the peak increases. Even in the other cases of the photoresponsivities, we see the same thing. Like there is a peak which keeps on increasing. There is a peak which keeps on increasing in this case as well. Now this effect is because of the quadratic Stark effect. Therefore, we had included the quadratic Stark effect. Now this effect was given by J. Stark in 1913, according to which you have electron and hole coulombically bind together. When you apply the field, the exciton binding energy basically increase, and then these carriers basically have extra binding energy, which comes through this particular term, which is B into F square, where B is the polarizability, and A gives the exciton diameter. This effect is seen, these effects basically is most common in dissociation of two-dimensional exciton. In this particular paper, they have shown how this effect is more prominent in two-dimensional materials like WSE2. Similarly, our depletion region, which is around 120 nanometer in thickness at zero bias, is like a two-dimensional sheet. Therefore, Stark effect for bound exciton in depletion region is quite common, quite normal. Finally, in order to fit our data, we have these two requirements, which is the inclusion of electron-hole interaction in Franz-Keldysh model and the inclusion of Stark effect. These two effects were considered in a model by Merkulov et al. Therefore, we utilized this Merkulov et al. Model to fit the data, and you can see that we got a nice fit with R square of around 0.98 for 0.98 to 0.99. And then finally, when we calculate the VL, now I want you all to note that VL is basically the only parameter which is varied in order to fit this highly nonlinear spectra, using only first principal values for gallium nitride, first parameter principal values. Finally, when we plot this V local versus V, we get this straight line. When we fit this these VL versus V curve, we get this straight line, and then this line corresponds to this particular equation. VL is equals to C V minus VBI, and then VBI, which we get through this plot, was actually equal to the VBI which we get from CVI. Therefore, the CV data matches well with the VBI we obtained using the XFK model. And this line basically can give you if the location at which you are doing the measurement is a hot spot or a cold spot. So basically, if C parameter is equal to 1, that means the location on which you are doing the measurement is neither a hot spot nor a cold spot. Or if it's smaller than 1, as seen in this particular case, it will be a cold spot. And if it's greater than 1, it will be a hot spot. Finally, at this particular location, from Silvaco simulation, considering uniform surface resistance, no defect concentration, and then equal impact ionization values for electrons and holes, we expected a field of around 1 megavolt, and according to which we draw this 40 volt curve. But we obtained 0.5 megavolt, which signifies that we were on a electrostatic cold spot, which signifies that the surface potential at this particular location is higher than that of the anode. This could be because of the varying depletion width, as we noted from different papers that the depletion width can actually vary from 20 to 30%. And then this could also be the case of partially removed regions, that is due to surface damaging. In summary, we can illuminate any position on the device, and then we can measure the field at that particular location. So basically this is a local field measurement method. Secondly, we noted that exclusion of excitonic effect in gallium nitride for field measurements would drastically undermine or overdetermine the field measurement results. Therefore, we definitely have to include the excitonic effect while modeling gallium nitride responsivities. Third, we noted that field simulation undermine the realistic effects, and thus a measurement technique like this would be an amazing, non-destructive, because it doesn't harm anything to the device, accurate. It will give you a very accurate value, and the fast way to measure fields in power devices. 2D mapping of fields using this method is currently under development. This is my team. I want to thank all my team members for helping me out. And then I want to thank Dr. Rajan's group student for growing the device for this study. And then we are thankful for the financial supporters. Thanks a lot for hearing. And if you have any questions, please reach back to me, or you can contact us. You can read our paper. And then if you want to collaborate, please contact us. Thanks a lot.